Swayam Prabha. Digital India. Educated India.
Let's get started, yeah, because otherwise we. Okay, so I have been thinking that, yesterday we have seen this transient design situation, and we have ended up, for example, somebody of you asked, we ended up yesterday calculating a critical moment for different situations. And some of you ended up saying, okay, what we do with this critical moment? Well, generally, whenever we perform a structural design check, we have on one hand a resistance, and on the other hand, we have a action. And we have to compare them. So that critical moment has to be meant as the resistance versus a certain failure mode. And the action, for example, we have seen how to calculate with the example. But I thought it would be profitable. It may be concept that you already know, but it's good to repeat and to go with a harmonized language so that at least in the development of the classes and of the course, we understand each other. So in this morning, we will deal with the basic principle of structural design according to what is now the format, which is, I would say, more or less recognized by the structural design codes worldwide. There may be some differences in notation, in numbers, and so on, but the philosophy through which we approach the structural design is always the same. And I put here two figures. Well, one is a rendering, actually. On the left-hand side, you have the Pantheon in Rome. Well, the Pantheon is the oldest still standing concrete structures. It's not reinforced. Okay. And the other one is a rendering of, it's called Burj Dubai, I think it's called now, which probably still will be for some time before they finish the Jeddah Tower or something like that. But still is a remarkable building. It's more than 800 meter tall, and it's made of reinforced concrete. When I said the Pantheon is the still oldest living concrete structure, the fact that it's not reinforced is not the case, because every now and then in the press, especially in Italy, you find, oh, the Romans knew how to do the concrete because their concrete is lasting for 2,000 years, and see the structures today. Well, first of all, this concrete structure does not have reinforcement. So you have already eliminated one of the durability issues of the reinforced concrete, which is the corrosion of the reinforcement. On the other hand, never forget that like a structure cannot exist without a material does not have sense without a structure. So speaking about Roman concrete and does not going deeper into how that Roman concrete was used, it's a little bit meaningless. As a matter of fact, the structure of the Pantheon is a very thick cylinder wall, and there is a dome on it. Well, the dome is a structure which mainly works under compressive forces. And compressive forces are what concrete is naturally, good for. Concrete is not good in tension. For this reason, we put reinforcement. But also in domes and in shells, there are some tensile stresses, especially at the edges. And in domes, what does it happen is that, there is a part of the dome, the bottom part, where the hoop forces, because of gravity loads, this structure just withstands its gravity loads. The hoop forces can be tensile. What did the Romans do? And this is an interesting fact because it means that they knew how domes work. And it's not, oh, sorry. If you go inside the Pantheon, the dome starts at this level here, which I'm pointing with the pointer. Whereas if you look at it from outside, you see the dome just coming out here. So in all these parts, which is the part of the dome where the hoop forces can be tensile, the Romans put a confining wall, 2 meters thick. So this is the reason a material does not exist without a structure, but that structure could not have existed without the material. Because what the Roman did, and it's very wise from the point of view of using a material, nowadays we will call it functionally graded material. You know, this structure has to withstand basically its self-weight. So in the dome, the Romans used concrete made with pumice aggregate. Pumice is a volcanic rock. When the lava from a volcano arrives at the sea, it rapidly cools and it forms a very, very porous rock. And if you pick up a piece of pumice and put it on water, the pumice floats. So it's very light aggregate. So they used what we will call today lightweight concrete in the dome to reduce the weight. But then, as long as they were going in the wall, you see there are 3 sections in the wall. In each of those 3 sections, you had concrete made with a different type of aggregates. It's lighter at the top. There are some crushed bricks in the middle. And there is travertine rock, which is very hard aggregate in the bottom and in the foundation. So see, they had the structural concept, the fact that they had hoop stresses and they had to confine it. But they also selected the best material for these applications because depending on the level of stress that you have, they provided a material with a different strength. The other thing that you have to take into account when they speak about durability of Roman concrete, how is the stress level in this structure? You have a 2 meter thick wall just supporting itself. What you can expect, really a few megapascal of stress. Then the structure, there is no reinforcement and it's in a urban area. There is some traffic, but not that much. The sea is about 30 kilometers, so it's difficult that other aggressives arrive. So really, this structure is like in a protected condition. So the durability of that material is because it has been employed in such a way that it's compressed, there is no reinforcement, and the exposure condition is such that it does not harm the characteristic of the material. So this is always what you have to take into account. And this to bring to you the attention that this sentence that is written here, structures and structural members, so the wall part, the wall complex, but also each part of it, it's not the case. You know, when you read a code, the words are not put there by chance, because sometimes the words are a matter of long discussions and debates and votes and fighting sometimes and so on. Structures and structural members shall be designed. So the first thing is that you design, then constructed and maintained. The fact that you have these 3 verbs, you also identify 3 main, let's say, stakeholders which have the responsibility. The designer has the responsibility. He has to correctly design the structure. The constructor has the responsibility to put into place what the designer has designed. And the owner and the user must comply with how the structure has been intended to be used. If you have a tool and try to use it in the wrong way, sooner or later it will break. That is the same in structure. In such a way that they adequately and in an economically reasonable, as I said, I prefer not to use economic, but cost-effective way performed during construction. This is very important, as we have seen in precast structure, because also the construction stages are moments of the service life of the structure where you have to guarantee safety and serviceability. Service life and dismantlement. So this is the concept that, you know, you have to take into account all the service life of the structure, and you have also to consider the fact that at a certain point you can dismantle this and make some other use. well, then there will be somebody else which will design the dismantlement and so on, but you have to take this into account as well. Not that much. It's, I would say, it's close to seismic regions. There has been, for example, Naples is less than 200 kilometers away, and Naples is a strongly earthquake region. There has been in 2016, I think, an earthquake northeast of Rome, which destroyed severely mainly a village there, but was not that felt in Rome. Yeah, the Colosseum. Yeah, but it's not that. It's not that was no, it was not earthquake. That was because during the Renaissance, the popes, to build the Renaissance monuments of Rome, used the Colosseum as a quarry. Okay. Then there are other important statements. You see, the first thing that is said is that they shall remain fit for the use for which they have been designed. This is an important thing because, you know, also when we teach structural design, we always teach, also yesterday I said, this is the critical buckling moment. And buckling is something that if it occurs, the beam breaks, really fails, meaning that does not exist anymore. But that is something for which we have to design, but that is something that we do not want to happen. Whereas what is called the serviceability condition is something that happens. So in some cases, or better, from a certain point of view, designing for serviceability is even more important than designing for ultimate limit states. We have to check both, but we have to bear in mind that ultimate limit state which attains to safety, it's something that we do not want to occur. Serviceability limit state which attains to use, it's something which happens. So the structure experiences that conditions 24 hours a day, 7 days per week. But besides that, we also have to take into account, and this we will see tomorrow, this has become even more important. The structure shall withstand extreme events, an earthquake, an explosion, some kind of events that you can imagine, but you know, it's very long return period. This is the way in which we statistically handle that. But can you imagine you are designing for gravity load, for live loads and so on, and then you design for earthquake? Can you apply the same design philosophy to the two cases? Because, you know, when you design for an accidental action or an extreme event like earthquake, you cannot require that the structure performs in the same way than under your gravity and live loads. The concept that you require for extreme events is that generally these extreme events are not forces in the sense of loads, gravity loads, weights, and so on, but are some kind of inputs of energy that you give to the structure, an earthquake, an explosion, and so on. So the philosophy that we employ is that this energy, the structure must be so, how to say, clever to accommodate them, to let this energy to pass through, damaging it, but not bringing it to collapse. So we accept the damage, but not the collapse. And these extreme events, but also frequently repeated action, you see environmental actions. This is something that when we go into the codes make some good statements, but then, you know, they lose sometimes themselves. For durability, in most of the cases now, what do we find in the code are some composition rules for concrete and some details. You say, okay, that's fine. If you do this, it's okay. Well, if you do this, that is the starting point for being okay, but it may not be true. Because environmental exposure scenario do change. And nowadays, we do not have one concrete. If you say, I want a C40 concrete, which is an extremely good concrete, You can obtain C40 concrete in a variety of ways, employing a variety of cements. And versus carbonation, those variety of cements behave in a totally different way, each one of them. So that does not mean anything that you want certain strength grade and a certain minimum content of cement with a maximum water cement ratio. Because you should specify what type of cement is there. You should specify what is the cracked condition of your structure. You should specify what is the CO2 concentration in the air, the moisture, and so on, just to make an example. But what do we want always is that the principle is that we have an action, which is the cause producing some kind of response in the structure. The response must not be disproportionate to the cause. You will accept that in a harbor, the ships hit the harboring structures. Well, you put some fenders there to limit that. But you cannot accept that if I go there with my surfing boat, I chip off the concrete. That is not acceptable because the cause is really minimal and so on. Then the codes have also stated something important, that as civil engineers and as structural engineers, we have always to take into account nowadays that what we do must contribute to the overall sustainability. Which, I will warn you, sustainability is not the CO2 footprint of a material, is not only the CO2 footprint of a material or the global warming potential. Sustainability is something much more complex and deals with structural design. Okay, so basically, which are the requisites for which we design our structures? We first of all have to address sustainability. It means that we have to guarantee that under all the possible combination of actions that we expect during the service life, remember that combination does not simply mean a sum. Combination is something which brings also space and time concept into place. But under all the combination of actions, you shall guarantee that the structure remains fit for the use. And fit for the use is a requirement, okay, that surely deals, first of all, with the user comfort. If you are in an apartment building and see that your slab is sagging too much, you know, because you are an engineer, that it's not a matter of safety, but you don't feel comfortable in walking over a floor which is deformed. But for the fact that probably the floor finishings, you may have tiles or other things, they may jump off. And if you have partition walls, depending on how they are made, they may be made of bricks and plaster, they crack. Or if they are made of cardboard and connections, the connections blow up. You see the cracks, you are a structural engineer, you see, don't worry. You tell your grandma, don't worry, it never will happen. But you feel uncomfortable because you don't want to live in a room where the walls are cracked. So this is the serviceability, first of all. The other thing is that there are some structural issues that, if you have an excessive sagging of your beam, what does that imply? Well, it might imply that your concrete has been excessively cracked. So you lose your stiffness. And if you lose your stiffness and the crack, you are loading too much the compressed part of the concrete, which will creep because concrete creeps. So if you increase the compressive stress, the concrete will creep even more and you exaggerate these deformations. And if you have cracks, if your structure is indoor, there might be no problem. But if your structure is exposed, there are issues of durability. These are all issues that you have to consider in the serviceability limit states when you design a structure. Then you have to guarantee structural safety. Structural safety. As my structural design professor used to teach us, He said, structural safety, look it carefully, because this is your penal responsibility if something happens. Serviceability, you need a good lawyer to help you. But it's likewise important as well. Structural safety, we have to guarantee the overall stability. We have to guarantee sometimes, also what we can understand as a, deformability. It's written there, but you may claim, well, you have just said that the deformation of a structure is a serviceability limit state. Well, yes, it is. The cracking can be a serviceability limit state. But think that you have a water reservoir, which is excessively cracked. And if the crack is passing through, your water reservoir does not contain the water anymore. It's leaking. So that is an ultimate limit state, which means that you cannot any longer use the structure. Probably there is no person in danger there, except if that water is some contaminated water. If it leaks through, it goes into the water table and there's issues there. Or if you have a container for nuclear waste, if it cracks, radioactivity can come out. That is an ultimate limit state. So the same situation, depending on the structure that you are dealing with, can be at the same time serviceability or an ultimate limit state. And the issue is that we design for serviceability and for safety with two different levels of reliability. That is obvious. We cannot guarantee that serviceability, something which happens regularly, has the same level of safety as an ultimate limit state. Also, take in mind that we deal with this concept not in absolute terms, but in probabilistic way. So ultimate limit state, we say that the probability of failure is on the order of 10 to minus 6, 10 to minus 7. It means that if we will be able to make 1 million structures all equal, well, we should expect that one of them will fail. The issue is that we will never see this because we will never make 1 million structures perfectly equal. Serviceability limit state, the probability of failure that we accept, probability of reaching that limit state is on the order of 10 to minus 3, much higher. That's true. It's something that happens frequently. Most likely the actions that we expect for those states are lower. And so we got it. And you see that once more, it's stated that structural safety shall be analyzed for all possible damage states and all exposure relevant. So there is always this remark that the structure is in an environment as it interacting with the environment. Then we have to guarantee durability. And once more, durability is something, it's really the problem where you see the merging of materials and structural concepts. Because you have a material, that material has certain durability characteristics, okay. But then that material you put in a structure, and that material in the structure will function in a certain way. So the durability characteristic of that material embedded in that structure, in that structural service scenario, will form the structural durability, which is basically, if you want to see in a very simple way, for how long time my structure will retain its performance at a level which will not require me to make a maintenance. It does not mean that your concrete does not crack, that your aggressive agents do not penetrate, and so on. This can happen. The issue is that you must be able to govern this phenomena in such a way over a certain time span, you will not need the maintenance. But you have also to understand that after that time span, you will need the maintenance. That is very important. And the other thing is we have to guarantee sustainability. As I said, sustainability is not only global warming potential. We made a study in, well, it was actually in Spain, and we were using a UHPC, or ultra high performance concrete, okay? Very thin elements. So the sustainability came from the fact that we reduced by 70% the quantity of material that we needed. We went from about 9 to 10 centimeter thick slab to about 3.5 centimeter thick. So it was around 60% reduction of the material. Very, very effective. But then we realized that one of the constituents, which was silica fume and the fibers, have to come from very far away. So the impact of the transport jeopardized half of the sustainability benefits. This is something that we do not have to forget. I am a huge fan of UHPC. It's not that I am saying that you have not to use that. But this is also something where the industry can work together with academia, because the responsibility of the industry is that, okay, we know that UHPC is a good candidate for certain applications. We also know that one of the benefits, one of the values of concrete is that its supply chain is very capillary. You find cement really round the corner and you find aggregates really round the corner. If we want to make UHPC as sustainable as regular concrete, the supply chain must be developed. And there is a lot of opportunity. I think I remember one of the students of Professor Ghet made a survey in India for the fly ash plants exactly for this purpose. Because then we have seen that if your material has to come from farther than 2, maximum 300 kilometers, at a certain point, your sustainability balance blows out in some way. Also considering that throughout the world, most of that transport occurs by trucks, and trucks use non-sustainable fuels so far in most of the cases. If it goes by railway, it depends on how the electricity that the railway uses is produced. There are countries where it comes from renewables, but there are countries where it comes from coal. And so, you know, it's a loop. So this is what we have to take into account. So sustainability is not that you say, oh, I am using a low clinker cement, I am using this waste material into concrete, and my concrete is green, and we are all happy. No. Well, how do you use that concrete in your structure? What do you make with that concrete? And then the supply chain can be likewise important. So let's try now to go to some mathematical formalities. You know, as engineers, we have to deal a little with that. So I have said structural design, it's comparing two words that have to talk to each other. On one hand, you have the action. I put there generalized action because we are, you know, inclined to think action a load. Well, in most of the cases, I would say it is, but in some cases, it's not. In some cases, can be the concentration of the chlorides in the water. That could be the action, just for example. So action is a performance demand. What do you want from your structure? And on the other hand, you have resistance. Resistance is not the strength of the material. It's a more complex concept, and it's not a case that the codes use resistance and not strength. In Italy, we have the drawback that we say the same thing with the same concept with the same word, so we are a little bit confused. We use resistenza for both, but resistance is a broader concept. It's what your structure is able to provide, to offer. So you have on one end the performance demand, and on the other end the performance capacity. So the easiest way you could work is to say, okay, my capacity must be larger than the demand, and I am okay. But there is a complication. The complication is that both the demand and the capacity are not deterministic quantities. They are, let's say, stochastic processes. So we have uncertainties in estimating them. And how do we, protect ourselves from uncertainties? We use a safety margin. We simply say, okay, I do not want simply that the capacity is larger than the demand. I want that the capacity exceeds the demand by a certain quantity. And this quantity is not fixed. It would be meaningless to fix it because the capacity and the demand could have different degrees of magnitude, different orders of magnitude. So it will be good to say, okay, I will accept that this safety margin is expressed as a percentage of the resistance. So if you work out the math, you have that you want that the action is not simply lower than the resistance, but it's lower than the resistance multiplied by 1 minus a proportionality coefficient. Now, if instead of computing the difference, which is the safety margin, so how far can you go, you compute the safety factor, which is the ratio between the resistance and the action, and work out a little math, you can say, okay, but in this safety factor, what shall I put? Why do I need that safety factor? Well, basically, I need the safety factor because I have uncertainties in estimating the action and uncertainties in estimating the resistance. For example, do you have an idea of, well, I don't know the exact number of Indian codes, but this room here, for which live load is designed? Okay, that is in India. In Italy, it's 3.5 kilonewton per meter square. So you already see. And have you an idea of apartment buildings in Europe are designed for 2 kilonewton per meter square? Okay. Have you an idea of what does 2 kilonewton per meter square? So can you figure out physically, what does 2 kilonewton per meter square mean? Don't tell me 200 kilos because it's the same. Okay. Can you figure it out? What does 200 kilos or 2 kilonewton per meter square mean? More or less, this is 200 kilos per square meter. Okay? I didn't call the girls because it's unpolite for the ladies to speak about weight. Well, this is 200 kilos per 1 square meter. But then you have, thank you guys, I appreciate it. But then you have to repeat this for every square meter here. So it's a huge party that we are designing our apartment buildings for. Well, as a matter of fact, we have also the furniture. If you have a bookshelf that not really you put not in the middle of a room, that is. So this is the physical meaning of that number. Or you have to imagine that it's a room flooded with 20 centimeters of water. That means. Where did that number come from? You hardly can tell it. Well, there are some social models and so on. For example, the Eurocode, the European codes, allows that if you have larger spans, you can reduce by a certain factor the live load. Because if you have larger spans, it means that you have larger living rooms and so on. And in a larger living room, you have less loads. You have more ample spaces. The Japan code is exactly the opposite, probably because they pack people, I don't know. So there are social living models there that at a certain point they were chosen and decided, but nowadays we hardly can tell it. And there are also, if you go into the codes, for example, there are some issues that are not covered. For example, in Italy, we have the snow load, but I think that for altitudes more than 2,000 meters, so somewhere in the Alps, the code does not say anything. So you must go to the weather stations and to check which was the average precipitation of snow, make some elaboration of yours. I was involved in the past in designing a car park for Winter Olympics in somewhere, and this station, okay, for Winter Olympics, you go to 3,000 meters and so on. And we did not have the number of the snow load in the code. Or once there was a grocery store, they had to store water. Well, you have the pallets with the packages of mineral water. Every cubic meter of water is 1 ton. If you have to store 3, 4, it's a huge live load. So this, just to show you that there is a huge variety of these numbers, and they come from different considerations and so on. So we have uncertainties. Well, for water, you can say, okay, water is water, and it probably is the only certainty that we have about the density of water, more or less. But other numbers, the action, there are models that we use to estimate that. And the same is the strength, and we will see, which are the uncertainties that we have in estimating the resistance. So what we do, we say, okay, since we have these uncertainties and we want to protect ourselves from them, let's not use a nominal value of the action, but let us affect it by a multiplying factor larger than 1. And for the resistance, generally, let's also affect it by a factor, but let's put it at the denominator. Let's divide by this factor, which is larger than 1. So we are not comparing nominal action and nominal resistance. We are comparing factor at once, and we strictly guarantee that the former does not exceed the latter. So it's a strictly less than, not less than, less or equal. So the issue is, how do we handle these uncertainties? May I walk? I feel uncomfortable in sitting for too long. How do we handle with these uncertainties? Because we are engineers, that at a certain point, we like to put our pen on a drawing, on a sheet of paper, and draw something and write some kind of equation. Well, we have the statistical tools. So, for example, we know that we have a quantity, a phenomenon which is characterized by some uncertainty. We use distributions here. So here you have basically the values that this quantity can have. And on the y-axis, you put the frequency of the events for which that quantity takes that exact value. So this is called the frequency distribution function. Actually, in order to arrive to this continuous function, you need quite a lot of data, which may never be enough. So at a certain point, you use this mathematical formulation and you see how to best fit it. Nowadays, with use of artificial intelligence, you can also, with models, populate with data your. The interesting thing is that if you calculate the integral of this function up to a certain value, which is this function here, that integral, which is the probability density function, gives you the probability that that phenomenon, that quantity, assumes a value lower than this. So if you calculate the integral of this function up to here, which is 0.5 for this Gaussian, okay, it means that the probability that this phenomenon and so on assumes value which go between 0 and x bar is 0.5, is 50%. Probability ranges between 0 and 1. 1 means certainty, 0 means. Well, for example, this model here is used to deal with tolerances. You prescribe a beam to be 300 by 400, you have to expect some tolerances. And from surveys made on the job sites, it has been shown that, well, these tolerances fulfill, respect, are very well fitted by the normal or Gaussian distribution. There is another distribution, which is very well applied to the strength of materials, especially strength of concrete, which is the log normal distribution. Well, mathematically speaking, it's a distribution where the logarithm is normally distributed. And the characteristic is, as you see, is that you have a shorter part on the lower values and the higher frequency distribution on the higher values. Strength of material, generally, it's good that we have higher values on this side, because it's good that we go a little bit more frequently on the higher sides of the. But so, if we want to apply these statistics to our safety check of a structure, what shall we do? Well, in an abstract world, if you talk to a mathematician, he will say, okay, you have your resistance, you have your action. Imagine that you have a population of data for both resistance and action. And you have some kind of criterion to match them one-to-one. Okay? So you can calculate, you have a population for the safety factor. Well, if you have a population, a reasonably good number of data for the safety factor, you can build up your statistical model and you calculate the probability of failure as the integral of this function up to the value 1. Because that means that is the probability that the safety factor is lower than 1. If the safety factor is lower than 1, it means that your structure is unsafe because the resistance is lower than the action. Well, which are the drawbacks? The drawback is that we do not have sufficient data for both the resistance and the action. And seldom we have a criterion to pair them, because in order to do this, well, the example that was in the textbook on which I studied was that imagine that you have to build up the basement for a monument in a square. So you build up several of these basements and you bring them to the lab and test them and crush them, and you know exactly the resistance. Okay, can be done. It's expensive for basement. The other thing is that you ask your main artist, which has designed this monument, to make so many replicas of the statue, and you just weight them. That is how will it work. Well, you know, it's true that it's rare to have this, but one thing in precast structures is that we do not have the possibility to really go for this full approach, but we can have something like that. As I was telling you, the day before yesterday, precast factories, especially for what they call special products like roof elements with strange shapes and so on, they must make regular tests, load-bearing tests up to failure of their element once a year. But so if you try to collect this for typology and so on, you might have a good database for the strength, for the resistance, and also for the action, because you have the weight of the bundles that you put. So in that case, you could have something like this. And then there is also the possibility of populating this database with like a Monte Carlo analysis. So you have your structural, who was speaking about software? You this morning, okay? So you have your structural model in whatever software, and you plug in some routines which tells you, for example, that the dimensions of your beam, they change with some kind of a probability distribution load, that the strength of your material change with some kind of log normal distribution. So you run tens of thousands of analyses, and you build up this database. But you will realize that if we would have to perform this for any kind of structure, it would absolutely be unpractical. So we accept to go, this is what we call the exact method. We are able to quantify the probability of failure. We accept a little bit less level of refinement in our analysis. And we start with an assumption which, as I will demonstrate to you in a while, will be very, very strong and incorrect, but we accept it as well. You see, we have resistance and action here. The resistance depends on certain variables. For example, imagine that you have a beam. Okay, what does the resistance of the beam depends on? Well, stiffness, well, it could be some kind of a resistance, but before the stiffness, what do you have? Sides, dimension of the cross section, first of all. Then, yeah, the strength of the materials. If it's reinforced concrete, characteristic compressive strength of concrete, characteristic yielding strength of steel. Okay. Then we have the action. What is the first action that any structure, each and any structure has to resist? Self-weight. What does the self-weight depend on? Density and volume. What does depend on? Dimensions. So you see, the resistance depends on dimensions, the action depends on dimensions. So we make the assumption that, well, this is the formality according to the Venn theory, that the variables which affect the resistance are not the same which affect the action, but it's completely wrong, because the dimension of the structure affect both. But this is just to handle the problem from the mathematical point of view. And to be able to say, well, I assume that I am able to build up separately a model, statistical model for the action, a statistical model for the resistance. Statistical model for the resistance is, like we have said before, you can have it experimentally or numerically. For some actions, we have statistical models. For climatic actions, snow, wind, rain, whatever, we have, because there are weather station recordings. So we have the statistics of wind, for example. So we could elaborate that. In some cases, we could have this. So if we are able to separately build up the statistic, which we can do if we accept this assumption that we know it's not fully true. If we are able to separately build up the statistics from, the conceptual point of view, guaranteeing the safety will mean keep these two curves sufficiently farther apart from each other, so they do not overlap too much. Because you see here, there is a region in which your resistance is lower than the action. And so the area under here is what dictates your probability of failure. So if you keep those two probability frequency density functions farther apart from each other, that area is very low, and it's something that you can accept. But still, this is in some cases feasible, but comes, well, nowadays with AI, even the computational effort may not be so high, except for the fact that AI servers need a lot of energy for cooling and so on. They need a lot of CO2 and so on. So it's not time and money, but it's the environmental effect, but it's not the problem. So we go to the so-called semi-probabilistic method for safety structural design, which is what we generally use, what is stated and recommended in all the design codes. And what does this method state? The method states simply, okay, let us accept that we will never be able to have these statistical distributions. We don't care of having them. We accept, most of all, because sometimes in the design, you don't have any information at all. You are anticipating, in a sense, what the reality will be. And we say, for the action, let us consider a value that we call the characteristic value, that in some way we can state is that value which has 5% probability to be exceeded. Is the so-called upper 5% percentile or upper 5% fractile of the distribution. In most cases, we don't know the distribution, but we accept that value to be the upper 5% percentile. Well, what does it mean? It means that we are picking up, we are selecting for our design calculations a value which is sufficiently high, not the highest possible, because mathematically speaking, this has no limit. So we have to accept to, at a certain point, make a cutoff. For the resistance, we applied the same way of thinking, but simply we stay on the lower side. So we pick up the 5% fractile. So it's a value that we deem has 5% probability to be lowered. So if you go here, basically we pick up a value on the resistance which is sufficiently low, and we pick up a value on the action which is sufficiently high. Yes. Tradition. No, there is something, because that complies then with those percentages that I say 10 to minus 6, 10 to minus 7, and 10 to minus 3. So there is some statistics behind that. And the other thing is that you have always to consider building a structure and using a structure is a human activity. So there is some, I will say, cynic reasoning beyond that, but it's not exactly that. There is some reasoning that this human activity, you cannot guarantee, or you do not want to guarantee that the consequences of this have a higher level of safety than normal living. As Winston Churchill used to say, we all die, and that is what defines the condition of living. If we will not lie, we will not be able to define living. Philosophically speaking, you define something by the opposite of it. Normal, yeah, log normal, yeah. Strength, compressive strength is log normal. Compressive strength is log normal, yeah. Actually, well, it was like this. You see, okay, it's like this. Well, as I said, this is a distribution where the logarithm of your strength is normally distributed. So you have to go through a double mathematical passage, but then in the end it's very easy. But the good thing is that you see, if you have to pick up here the characteristic strength, you have a lower difference. This is, this is the most probable value, which is not the average, because the average can be shifted a little farther apart. So here you can also appreciate, or the median, basically. The median is the value to which the 50% probability corresponds. So the benefit of this log normal distribution is the fact that your characteristic strength is closer to the median value. Because what you get from the lab is an average. And then from the average, you have to go back by a certain coefficient, as it's written here, which brings you. So the log normal, which is, we are not using the log normal because it's, better, gives us advantages. It's because the experimental results of compressive strength of concrete appear to be distributed like that. Yeah, well, we have to accept that if you write the function, it has values on the negative, but they are so low that you can neglect it, or we accept a curtail at x equal to 0, because we are dealing with strength, and the strength is intrinsically a positive quantity. So as I said, once we have identified these two values, the characteristic values, we put them into the inequality that we wrote before. And so we require that the safety factor, which is the ratio between the two characteristic values, must be higher than a fixed threshold number. This threshold number we split into a strength contribution, a resistance contribution, and an action contribution. And we denote the ratio between the characteristic value of the resistance by its own partial safety factor. This method is also called the partial safety factor method. Because you see, you have one factor for the resistance, one factor for the action. This we call the design value of the resistance. This we call the design value of the action. So why did I want to put this? Because in the next classes, we will frequently speak about resistant design bending moment, and so on. And you will have always this subscript D here. So that is the design value. The design value is already a factored value. So this has to be clearly taken into account. But there is a but. As I was saying before, we never build a series of structures. In precast concrete construction, we can build series of elements. And this is the advantage, because we can have much more information on the reliability of the performance of our elements than we do have in cast-in-place concrete structures. We do have series of elements, but the structure is always unique. As I was saying Monday, a designer, a structural engineer, a structural designer cannot say, oh, I'm using this beam, and this beam, according to what the factory says, has this load-bearing capacity. Yeah, that is an information that he uses, but he's responsible then to check that that beam in that structure is subjected to certain bending moments, shear forces, and so on that comply with that. So the structure is unique, and you don't test it up to, you can test it up to some serviceability level, but you don't know what is its actual margin. The other thing is that we use a model to design our structure. We use actually different models, and we will see now in a while. What is a structural model made of? Well, first of all, there is a geometrical and kinematic model of our structural element. We are always used to think of the Bernoulli model for beams and columns. That is a model that luckily those kind of elements very well obey to up to failure. But that is a model. It implies that the cross-section remains planar, and from that assumption, everything comes in a very clear and elegant mathematical formulation that we can easily handle. But that is a model. And as I was saying, if we have rectangular beam cross-section or more or less compact beam cross-section, that works pretty well. But if we have a very thin-walled open cross-section, does it work as well, or shall I accept that that model has some larger uncertainties? You see, in geotechnical engineering, in this equation here, they put in the middle another coefficient, which is the uncertainty of the model, because soil is a much more uncertain material than concrete or steel can be. We accept our models to be, to be absolutely certain, deterministically certain. So the coefficient of uncertainty of the model is 1. But in geotechnical engineering, there is a coefficient which is the uncertainty of the model as well. So then there are the boundary conditions, as we have seen this morning for connections. The boundary conditions, when we design a support, a roller, a fixed edge, okay, for us it's an idealization, but that idealization has to correspond to something that you make in the reality. And it's a twofold mechanism. You must realize something that respects which are your assumptions. But the way you realize it also determines how the stresses will go. So you govern, in a sense, the flow of the stresses. And then we use some constitutive law, linear elastic, or some other kind of models, which are generally uniaxial model, because the beam we consider a 1D element. But concrete generally experiences multi-axial stress states, and not all of them can be in favor of safety when you design that. And then we have to agree upon a limit state definition. Is the example that I made to you before, cracking. in a beam can be a serviceability limit state. In a reservoir, it can be an ultimate limit state. Are we going to guarantee that crack width in the same way with the same level of reliability and safety in both structures? Or shall we accept for the beam something more relaxed and be more strict on the reservoir? So these are always concepts that you have to consider. Well, I just summarized it here, you have on the slides. These are some equations. This is the typical equation of the beam model. These are the equations of the 2D plate model that you can use. These are some examples. Their pictures can be similar to what you have seen in this morning. So what is a hinge? What is a support? Are connections like these really hinges, or do they have also some kind of stiffnesses? And how do we model and how do we quantify that stiffness? The test that we have seen this morning, for example, they can allow you to quantify how far that connection, which is the beam supported on a corbel with a dowel, is fully in, or you have to put into that some stiffness. Because you know, what is the outcome of this? Well, your stresses inside the elements can change. But also, depending on whether your connection is simply this or has also some other stiffness. If you go into dynamics, which is important for earthquake, your frequency, the frequency of the vibration modes can change. You might have a stiffer structure, and stiffer structure may also mean that the inertia effects are felt stronger. So may not be always. And these are some examples of limit state definition. What is limit state? See, this is a ultimate limit state. You see this sagging by probably 10 centimeters, but still it's not broken. Sometimes when we think of ultimate limit state, we think of something that is broken, like this. But here the structure is not broken. But surely, you know, even if you remove this load, the structure will never go back to its original position. So in the standards, in the codes, you find 4 different levels of limit state. Well, one is the operational limit state. It means that under a certain scenario, your structure continues to be fully usable. Not only the structure, also all the equipment and fixings that you have inside that. Well, here it's not clear. It's like there is written Joe here. It's like a hamburger counter and so on. But think of a hospital after an earthquake. I was just watching some weeks ago, there is a series on Amazon Prime, which is every minute counts, about the Mexico City earthquake in 1985. And it starts exactly in the hospital there, which partially collapsed. A hospital, you want it to be fully operational. Not only the structure, also the access roads to the hospital must be fully serviceable. But not only the structure, also all the equipment that you have inside. And this is the reason for which nowadays, for example, in earthquake regions, San Francisco and so on, for hospitals and other strategic buildings, you use base isolation. Because you can guarantee operational limit state for the structure without base isolation. But then it's very complicated because you should fix your equipment very strong to avoid that they are damaged. And the equipment that you might have may exceed, from the human point of view, surely they exceed the value of the structure, but also economically speaking, they can be much more valuable than the structure. So this operational limit structure, we always consider for very specific strategic structures. Generally, we consider the damage limit state structure. What does damage limit state structure mean? Well, it means that, for example, our shop closes for a few days because probably some electricity ducts have to be fixed, the gas pipes most of all. And there are some minor damages which do not compromise the structural safety. They might be just functional or aesthetic. So you have to fix them, you can fix them, and your building, your structure, everything becomes fully in service almost in reasonable time. So it's called a limit state of damage because you accept some damage, but this damage has to be easily go straight forward for that. Then we have this true limit state that most of the cases we merge together are the life safety collapse limit state. So your structure has suffered very severe damage, but it retains the capacity to stand. So at least, supported with some false work. Whether it is repairable or not, you have to have collapse limit state. It means on the verge of the collapse. It's not even questionable. But generally, we check this and accept that. So these are the already discussed them. Okay. So how do we do? Well, imagine that you are designing for timber structure, I would say, as linear elastic material. So what do we do? With a model of the structure where we do it. You see, A is X. We perform a structural analysis. What does it do? Simply supported beam. You have your loads, draw the force, and so on. So these are the general on the action side. So the characteristic of your cross section. You use your section models, draw the distribution, and you have the maximum tensile and compressive action. That the maximum or minimum depends is lower than the strength of the material. So this means that you perform models here, a structural analysis model and the model. And you perform your at the level of stresses and strength. Well, say that more or less the same. They are more or less the same. They are going for the nonlinear properties of the material because you better mechanism. You already abate it at beginning. And this second level, when we design reinforced concrete structures, we make some assumption on the strength of the material. Compressive strength for concrete, maximum yielding. And we use a cross model. We say there is the stress block, there is the yielding force lever arm, and calculate the resistance. Or we use a truss model to calculate the. So resistance moment depends, but it's not the strength of the material. It's a different, a cross-sectional level. And it can be different if you apply the factor before or after. Because you calculate compressed part and so on, and that will affect it. Material first, the results are different. Resistance moment capacity or a resistance shear. Structural analysis as usual. And moment action with moment capacity. Action with shear capacity. Or a combination of them. In columns, you have a combination of axial force and bending moment. So you use the moment axial force interaction diagrams. In some cases, in precast structures, you have two-way bending. So you have moment-moment interaction curves at given levels of axial force. Then there is the third level, which is what we use, for example, when we make the plastic design with plastic hinge model. We have the strength of the material. We hypothesize a cross-section model and we calculate the moment capacity of the cross-section. And then we say, for example, we have a frame structure and we hypothesize that this maximum moment capacity is achieved in a number of cross-section, which is just equal to your degrees of hyperstatic plus 1. Because if you have a structure which is 1 times hyperstatic, if you form 2 hinges, it becomes a mechanism and it fails. So you can calculate through the theory of plasticity the load which corresponds to this mechanism, and you check that this load is larger than that. So we have 3 different ways, and we use them all 3. In some cases, also, intertwining them. For example, the way in which we calculated yesterday the critical failure of that beam, to which of those 3 levels belong, according to you? Well, we can say that it was a second level because we calculated a critical bending moment. But then in the end, what did we do? We correlated that critical bending moment to a load acting on the structure. So we could say that with the last passages that we made, we scaled it up to this level. Just to show you also how did we, can intertwine the two levels of safety. So these are some examples. Here it's what you were asking. If your materials are non-linear, if you apply your safety factor here, may not be the same than applying your safety factor at this level, like the US does. I think that is all. Yeah.